pleasure to introduce our speaker today. Radha and I have Radha's been a professor in at University of Washington since 2000, and he's presently the department chair. I would go through a thorough list of all the awards and best papers and one of the hours of substance today. Some outstanding work in network security. So with that, I'm going to welcome him.
Said he wouldn't need edits.
Good afternoon, and thank you very much for inviting me to the talk. And thanks to Jeff for trying to organize it since last fall. I have been here maybe 6 years ago in the computer science department for another large cybersecurity project related to robust and resilient mobile ad hoc networks. Most of the work that I'm going to present and most of the work that my group does is more along the lines of science of cyber, looking at the foundations and what results we can get, and also formulating the problems in the domain of engineering science. Earlier results have been more of algorithmic type, but the ones that I'm going to present to you are more related to connecting the attacks and the formulation of the attacks, and even including the mitigation in the context of what you would consider as the system side of the cyber. So it addresses the problem of, or at least makes an attempt to start addressing the problem of science of cyber security. I will put it that way. So that's the context within which I will present the work. So outline of the talk, cyber threats, I'm going to consider some of the properties of the cyber, followed by a system property that I'm going to make use of repeatedly to show that this framework is at least a reasonable one to address some of the problems. Then showing two examples which are well known, one in the set of wireless, another one is in the cyber domain itself, and show that how we connect the system side to the attacks, and then how we start reasoning about the formulation. And then I'll wrap up with future work, which is part of taking the next level of formulation, looking at the strategic interaction between the adversaries and the system, and then what we may be able to say about it. So this is a new initiative that is started. So threats, there are many different forms. Some of them come in the form of spatially distributed but persistent threats. that take place over the time. Some others are specifically targeting hardware or any other platforms that may go into targeting specific protocol assumptions, or may go into looking at the control aspects of the system. So it could be from the physical dynamic side or from the platform or discrete component side, protocol side, pure protocol. And other ones exploit specific vulnerabilities that go from one to other, and then they persist because of mistakes that were made in terms of the crypto and other structures that were formed. So I'm not going to be looking at the fault of the crypto. That is not the concern. We are also not going to look at specific protocol failure. We are going to look at those types of attacks. Their attackers seem to be persistent. So one time, the first type of attack is not something I'm looking at or going to be talking to give you any answer. So the type of attack that we are interested in looking at are across a larger time scale. It may be a single attack continuing with adaptive nature, or attacks of the time there is an entry point. From the entry point, there may be multiple different venues through which the next stage of interaction with the system and the adversary may take place. The next stage is interaction, as many of you know, is a stepping stone to move forward, or sometimes you may be just going back and finding another link. So I'm here showing the forward, but it's very much possible that there's a feedback to go back to try other links. So it could be social engineering or exploiting the specific vulnerabilities of protocol side, but in the interaction going forward to the next step rather than coming back and attacking immediately. So adversary here has a goal of not necessarily shaming you, but more of having a long-term interaction to gather and probably obtain certain information of that type. So there is, in addition to the interaction, there is underlying information dynamics that will be existing in this interaction. So one is the physical action, other is the nature in which the dynamics of information that will be. So this is a type of attack where you can partition into sections, and each section is a time period where the interaction takes place. If you were to look at the boundary, it looks like the next step is a disjoint jump. The disjoint jump takes place because of a decision that is being made at this level. So interaction took place, and then one party decides to make, is able to make a decision to go to the next level. So that will be probabilistic for both the parties, because if they know deterministic, then they would have worked it out offline. So the transition from one state to other is something that needs to be captured. So similarly, going along these lines, depending on what information they gather, the next stage takes place. So this is why each of the interaction is not predetermined. However, if there is a mechanism by which we can try to characterize or understand these methods, then we could answer questions of the type: should this system or the adversary, one of the players here are the entities that are engaging the interaction, should they decide to continue, or if they were to continue, what is the rate at which they are going to reach their desired state? This is the language from outside, but if you were to say, okay, if they were to continue, how long does it take before they go to the next step, or how long they have to be in this interaction stage? But for those who are observing what happened afterwards as a postmortem, you only get the train of the initial and the exit point. Inside substages may not be clear. For example, here, you could have been from any one of the three paths to go to the next level, and going from here to here could be any one of these paths. So the challenge then comes is that can we go back and find a way, given part of the information maybe, decompose and get different variants that are meaningful. So in the domain of systems, you could ask the question that can you parameterize these models if there is a way to do it at all? Because if you were to parameterize, then if you model one, then the other interaction is parameterized version of it. You don't have to remodel. But these are questions that we don't know. So bigger open questions in this kind of multi-interaction is, if you want to extract the questions, they are of the following type. First, how do you model the persistent notion? There is a time notion of time involved in it. You won't be able to model it. And then if you look at what the current status is, so someone would describe to me Sybil or wormhole or some kind of attack terminology, and they would say for wireless network I do this. Or if it is a false data injection for a certain type of application, I would do this. So there are mitigation methods for each individual systems. If you look at the large grid or any of the structures, simultaneously multiple attacks may be taking place. So what we would want to be able to say is that if they are persistent, can we first give an individual model and compose? Can we have some laws to compose these attacks so that when you look at the composition and you have represented the composition in a language, that the mitigation could also be developed in the same language itself. This is not to say that throw away the security side of the mitigation. I would probably incorporate that, but I may be able to give you additional results as to what my system should be performing. Because we design system for certain performance and there's a disturbance. This disturbance is intentional disturbance. So how do we go about arguing about building a mitigation or building a, if you were to say, corrective control or feedback mechanism to bring the system back into the operating point that you would desire, if at all possible. And so the questions of the type, can I compose, comes into that. But when you compose or propose a model in the statistics, typically in the engineering community and the statistics, we do go about giving confidence interval or quantify how far off we are from this specific model that we present to the community. So similar question arises here that if we were to propose a model and provide composition for this model, can we provide a way in the same framework to measure how far off our model from being correct represented in this language or in this framework. So we want to be able to find a mechanism to quantify uncertainty or deviation from the model itself. And the last question is, how do we design mitigation against composite attack models? So here, I could give you a reason why we would do that. Sometimes we get flu and we also get cold and a bunch of things, and we go and get a vaccine. Some of these vaccines have, they are essentially a cocktail. Maybe MMR is one example where there are multiple things. Simultaneously, one cocktail takes care of it. So I would ask from the security perspective that these are also some kind of infections and diseases. If that is the analogy, is it possible for us to come up with mitigation which can be treated as if a combined remedy for a set of different types of attacks, if at all possible? Other question we may pose here, that if we do combine and have a composed view of the attack, like in the SVD or the PCA analysis or even going into vector space, you have these bases and other elementary components. What are the primitive building blocks of your systems? So in the composed model, is it possible for us to develop a decomposition approach? It's not clear, but if can you develop a decomposition approach which gives me primitives? That when I combine the primitives, I get the variations of the attacks. So that kind of work is, right now it's open question, there's not an example as well in that domain. But we definitely know often in the software side, you do the variations of the software and then you get a whole sequence of different versions of the disease, right? Different versions of the models. So that is the question that we don't answer here, we don't, but that's something we would like to do. So looking at the approach that we would want to take for the persistent attacks is the following. That attacks that are persistent are time-based and they have a dynamics associated with it. This is a loose version of saying. You could say that this is discrete or continuous, or it could be hybrid system. Right? Any of the systems that have the dynamics could be either one discrete or continuous or hybrid. So if the systems are continuous interacting, then the interaction between the system as well as the adversary is also time varying and can be thought of as a dynamical system. So far, we are okay with the argument. But here's the loose observation that I mean, then I will formalize. The dynamics is associatable with some notion of energy. So if there is some dynamics, then I can always come up with, we have to show how to construct, come up with a notion of energy function or units of some mechanism like that. Right, so far so good. Now, given the energy, I'm going to, here I'm making a big assumption because the way I want to move forward with the results. I'm going to look at only the continuous case. The system that are interactive, but I can represent in the continuous model. Because those are the cases that I can completely say something about today. We don't know what to say about discrete or even hybrid at this point. So we look at those that admit continuous translation. So you want to go back and look at the interaction that may take place in a system. There is an observation period which is called the system information that is gathered by the adversary, which mounts the attack scenario which goes as an input to the system to drive it. In addition to, so this is the model interaction abstraction between the system and the adversary. This is not to say the system dynamics is only this. System has its own dynamics associated with it for the performance of it. So this is the other layer of interaction that is coupled with the system dynamics. So we could represent in the form some function of input to the system and there is an output. But this output is gathered fully or partially observed by the adversary. I'm permitting here the adversary has adequate enough and it has a version of it. That's why it's not simply the output of it. Some version of it goes into it, whatever that it is able to observe. That part. Then there's a output of this adversary's action which goes as the set of actions for targeting the system side. So now, unlike the original model in the absence of an adversary, the input to the system here is a bumped up version of it. It includes the dynamics plus the adversarial external input that goes into the system. So these are the two components that goes in. So the question is that, okay, so we can draw this figure, but to be able to move forward, how do we relate back to the energy and how we make the argument? So this is where the first question comes in. And we borrow a little bit of the classical results and quite heavily translate to the system side and use it. So the property that we are going to use is from the circuit side, which developed further into the passive systems. So this is the classical notion of the passivity. So a system that has an input and an output, then the power that is supplied to the system is defined as input time output. This is, if you know the circuit side, this is pretty straightforward, that we equals IR and the equations, we use power equations. But we want to be able to bring the notion of passive property that the system cannot generate energy. If you give the energy, it may dissipate the energy, or it may preserve the energy, but it cannot create additional energy. So this is a property that I'm going to repeatedly use to be able to make a case about analyzing this system. So first property that I'm going to use is that if somehow I can come up with the storage or the energy function, it's called a storage function, but here energy function. In the classical system, you have half V square some format, you know this. So here it's a V such that the power that is output of the system is less or equals to power that is input to the system. So that's a property we have, this is standard property. Another additional property that I have is that the system is strictly passive, so I want to use another property. If we can not only find the energy function, but we are also able to find the D function, it is 0 at x equals 0, and then it is greater than 0 at above a certain x. Such that this condition satisfied. So now look at it. D is positive for practical purposes. And I'm taking some positive quantity out, and the system still satisfies the inequality. So it looks like this system was excited and willing to generate enough power by itself. I want to be able to bring this property to show that even if I take out, the system still satisfies this inequality. So the added power, I can take some out and still the system will be passive. So you can ask circuit. So this intuitive feeling is actually very much valid if you go further down to the typical LC circuit and RC circuit. Here, the system is passive, energy is conserved, assuming the losses are removed. So it has oscillatory behavior. On the other hand, with the RC, you have strictly passive, eventually energy dries out. So the D is what I mean per unit radiating or spinning off. That's the power that is being dissipated, right? Not radiated first. Okay, so this is the notion of passivity in the VLs. Now, the reason why we went for passivity is the following: that under certain conditions, this allows me interesting properties. If I can represent a system as passive, and if I have another system which is passive, when I compose those systems in parallel, the result is also passive. That you already know, RC circuits and composites. You already have those systems. But in at the system level, similar properties hold. The next thing is that if the system is strictly passive, if I put another system which is passive in a feedback way, negative feedback, and I get an additional property which is more than just the passivity. So what it does is, it guarantees me that eventually things taper off and things are dissipated. So that means this system is drivable to my desired state. Let me put it that way. But these are properties that I would like to have, and then I show you that these properties are actually holding for systems that I'm going to model from the side. So now the next quantity is that, okay, this looks like control terminology coming into this, so why do you care? Because the model may be not well quantified. So we want to be able to now say how I quantify how far off your system is from the passive, because we need to be able to say that, look, this is the additional amount of resource you need to put to this system to mitigate against adversarial. So you did passive model and you are going to go through some process, but that is not going to essentially bring the system to the performance that you like to have. So what's the additional amount of resources that you need to handle? And this is a intuitive way of explaining, but this is actually what it is, and it shows you how to quantify what additional things you have in terms of dynamical system handling itself. So what is this property? So there is a specific type of passive property we want to look at. So I look at the output side, and output side, this you can see is the power at the output side. Output is y times y, or y transpose y. That's a non-negative quantity. And so this is rho. Depending on the sign of rho, I'm going to add or subtract something out of it, right? Power. Otherwise, this quantity is the input power to the system. So now there are two notions. One is the excess of passivity that you have seen in the past. I said strictly passive if it is minus d of x. You will recall that, right? So if it is rho is less than 0, the system is excess passivity in the sense you could take some out and the system is still passive. So this is excess passive when rho is less than 0. And shortage is that, oh no, now the problem is you can't take out, but you need to put a little bit more effort to make the system as a passive system. The system to start with was not passive, then we had to add a little bit more to it. This adding and subtracting terminology is easily done in the controls domain and system domain, and this is essentially put in the feedback side. This is it doesn't have to be linear control. It is a way of. So is this okay so far? This is just a foundation. So with that, now I want to go to a cyber or the pure wireless or wired network domain and take a problem and show what it means to this particular problem. And the rest of it is to explain what the problem is. Many of you probably know, so that's why I embedded the attacks in one figure. So here is, let's say, a node. Source here, intermediate multi-path route. It could be wireless or wired, it doesn't matter. So first type of wormhole is called out-of-band wormhole. The idea in the out-of-band is the adversary listens to the attack at the intermediate node. It could be near source, it could be anywhere. It data. It has a pencil beam antenna or some directional antenna through which it can actually bypass or violate this multi-hop delays. It can directly transmit to a node. Now look at this transmission. If you are familiar with the network formation and the neighbor discovery protocol, so this transmission will be a hello message from one of the nodes. So this node typically would only go into the radio range of the next node. But by having this transmission very fast speed of the wave, like EM wave, so the speed of light, so it looks as if it's a neighbor of each other. So this node may now respond back, and all this person has to do, adversary who is listening to, is to transmit back that message. So crypto doesn't get violated in this one, but the message was transmitted. So this is a wraparound. This is an old stuff. This mapping. These two nodes think as if they are next to each other, right? So this is one version. This is on the wireless. So let's go to the wired version. So these two intermediate nodes may collude. The other nodes, which are in the intermediate part of the routing, may be good nodes, and they may not have anything to do with these two colluding nodes. However, these two colluding nodes now may set apart in such a way whenever data comes. There is a shorter path, but they take this specific path by structuring it and then give an impression as if that is a path. So this structure, what is called the nodes that are actually in the network, colluding and creating this route, is called the in-band wormhole. So one is the outer band, but here artificially created in-band. So they are having prior works in the signal processing community, for example. They look at the data, they look at the spectrum, and based on the Fourier transform, they will identify whether in-band wormholes or they are not. So they are having different approaches. Okay, so lots of literature materials there. I explained to you what happens with it, and now let's see what you can do to deal with it. How can you defend against this? So people have studied about how to deal with it. In 2003-4, Edinburgh and Each Pool, they came up with a couple of very clever ideas for this system. First of all, they said a packet, you can put a limit on how many hops it must be. So you are putting a leash on the number of hops. You can also say a packet should not be traveling for more than a certain amount of time. So you can put a time leash. So this whole class of spatial domain or the time domain bounds or the leashes or thresholds are called the packet leash class. So this was done by Eaton and David. But it's so essentially this node is a sender at time 0. It transmits a packet, and then the delta max is the threshold. When it is reached, you drop the packet. So essentially, how does the packet get dropped? Packets don't get dropped in the air. They have to be inspected by an intermediate node. So this node inspects the packet timing, and then it looks at it and says, okay, this is a stale packet and drop it. So that's the defense mechanism. If the packet has here delta max over 2, it's a valid time, and the packet is accepted and continues to be forwarded. Fair enough, right? So now, if these two nodes are far away enough, and the transmission took place here, and this node inspected the transmission and it exceeded delta max, then it will throw. This is okay, so wormhole, way of dealing with wormhole is to put a leash on it. But the challenge is how to use delta max, that's a different problem. Okay, so this is a monitoring, system level monitoring that you can deploy at the protocol level, and it could be very well sitting there. So now, what do we want to do? Okay, system level protocol is there. Where do you want to go with the wormhole? Wormhole is essentially, if you look at it, what it has done is to somehow reroute or force route it's essentially flow redirecting attack. There are quite a few other attacks which do the same thing. But the whole class of these attacks, the fact that its wormhole is not important, what is important is they are flow redirecting attacks. Right? So they affect your throughput and other parameters. So we want to be able to ask the question that, okay, the solution is fine, but at the network level, can we formulate this problem and then understand it? Because then we can talk about performance and also incorporate the mitigation method, but we can then start talking about how do we choose the parameter and the stability of the system and how quickly we react. So, model, we want to be able to find out the congestion links for the following reason. If there is a wormhole and you detect it, two things happen. When you detect it, you drop the packet. The packet was good, it was dropped. Then what happens to this packet? It has to be replayed at some point. I mean, it has to be retransmitted, right? And if I false alarm twice, throw the packet away, again it's a problem. If I detect it correctly, it's good. If I misdetect or create a false alarm, then it's a problem because throughput goes down. And on top of it, when you see a path in van wormhole, you redirect your flow. So the detection does not address the fact that how do you redirect the flow. Because when you redirect, you are going to introduce additional delays to the system. So that you don't get captured other than the fact that we say, okay, I will detect it for you, I don't know what else I'm going to do. So this probably gives you a framework to go over asking what we can do. So the flow base, many of you look at the system. So on the top, what we do is to decompose this in an additive way into 3 layers. The first one is the network flow allocation. This is the routing matrix and standard. You give the pricing of the intermediate path. Using the path pricing, you come up with an optimal solution by iterating over time, right? So it should be flow allocation and your optimal solution for group. However, when the output comes in, you want to be able to translate the output and feedback to compute the link delay parameters, because then I have to adjust my flow based on some tunable knobs, right? Then one of the tunable knobs is the link delays. Other one comes because of the detection and false alarm and other components. So I have to also incorporate those parameters. So these are the components that we have. First is flow allocation, link delay, and the link price due to detection. This is where I clump all the quantities. We could have gone about doing many different sub-layers, but no need, for the reason that if I show you some of these are passive, then I can add them in parallel. So I can give you a superposition result instead of going into all layers. I can also go into other solutions. So the main idea here, the simpler version is shown, but the result is true even if the simpler version is relaxed. So the assumption here that all the sources, the sum of the rate is constant for this formulation, but the rate, total rate, bit rate doesn't actually constant. It's almost look like some kind of equilibrium satisfaction, but for this model we assume that it may be different flow rates, but the total flow rates is constant. So this is the assumption from different sources. It could be any source. And we simply represent it as one peak source and then one peak destination. In between this is multipath. I could draw an intermediate multipath network, but the idea is that this is at the very top level view of the system. So if you look at the price of the path, if I take a path, essentially my throughput is the one which I'm worried about, right? I want to get the packets through. So I ask, what are the components that are going to contribute to this price? Essentially, the link delays will come in. And then any activity that I do because of monitoring and the packet dropping, or even if I make a misdirection, it goes somewhere else and I'm going to pay everything. Right? So these are all grounded together. That is a path price for taking a specific path. And there is an optimum for given set of prices that you know. So the main result that we got was the following. If the total rate is R, then if I look at any link Q and set up the path price as QP, and this is the equilibrium point, the input-output figure, so here is we have the Q minus the Q star, and then here would be my R. So if I look at it, that system is passive. So this is one result. This is for the overall flow allocation one, not for link, not for the wormhole. So this is a standard. I mean, this part of the result is Murad Ashal's result, who took the network flow and converted that to a passive system in Fibo solution. So this is, I mean, the version what we have can be definitely derived from what he was able to say. So an interesting argument here is that at the optimum or the best situation where you cannot move any further, you don't move any further because even if you go to some other path, you know all the paths. You don't take any one of them, but you don't have any advantage taking any one of them at that point. All of them have the same kind of delay if you were to choose. So that's why specifically we talked about what the equilibrium notion is and then what is the rate that's allocated to that. However, that is just for the top layer information. I want to show you just from one component how to construct the following. See, wormhole link, I told you, for the packets will be dropped and all those things happen. I have to show you, I can generate a storage function and it satisfies this, the power generated meets some kind of inequality that I need to show. Right? So how do I construct it? The construction that I show you here is valid for link delays and it's also valid for all in-band or out-of-band components except that we change one parameter. So I'm going to explain for the out-of-band. Let's assume that for link value, one link that has probably a wormhole sitting there. You don't know that link has propagation time alpha L, that is given. But then the packet dropping probability of an adversary. So adversary has a goal not only to create problem to you, but to do so such that the detection is minimized. So it's not simply, okay, whenever a packet comes, you randomly drop. There's a strategy with which the adversary will do. So people try to study this stealthy detection, minimizing detection versus creating count. They're having a set of work in a completely different domain, and what people have shown is that the exponential or memory-less kind of attack would be very good for an adversary of that kind. But here's an argument though. If you have a large flow versus a small flow, let's say if I send one or two packets and those packets drop, I have a problem because I shouldn't be having congestion where the lower rates. So the packet dropping intuitively should be proportional to, you can show that detection versus proportionality. It should be proportional to the flow rate. More flow, maybe I don't catch you as the problem, maybe it can be from congestion, right? But I can state it if I have more packets versus I don't. So this PL, the link packet dropping probability of the wormhole, that can be, that's something we don't know, but that's a quantity that you would like to be able to find. So then the delay due to propagation times the number of retransmissions, because if it is dropped, assuming that each of them are happening independently, so this independent assumption is built into this geometric kind of model, then you can compute the delay as a function of the following type. This is the probability 1 over 1 minus the standard retransmission cube model that you use. So this is giving you an idea about how to compute the delay. But here is the interesting part. For all of the link delays that you would do for any of the rate limiting attacks, the storage function of this type, you could construct other storage functions, but you just need to have one function to show this is passive. I can compute one function and show this satisfies the passivity, and then I'm done. This system is indeed passive. So that is doable by looking at this. If I take the derivative is R naught minus f of r, and it is guaranteed if it is increasing r. So because I just need to show that this is going to satisfy the plus switch, and then this quantity is going to increase. So the delay will increase with the rate. That is not a problem, because the fee will increase with the rate. This is the argument that we need to give for same level of detection. I can still increase the number of packets that are dropped, and I achieve stealthiness or whatever property. If that property is not there, you can simply make an assumption. But having the avoidance of detection as a criteria shows that you can proportionally increase your fee R of L. So if it increases, this quantity goes down, 1 over this goes up. So f of RL is going to increase as long as adversary is not static one, just deterministically dropping. Is that okay? So the growth of this translates to the growth of this. And hence, if I look at larger rates, they are going to be greater than the smaller rates, which is going to be zero. So this one is that okay? So this is the main argument that I need to show that I'm going to get the function of the criteria, and then I can show the differential parameters. So now the deviation from the equilibrium can be interpreted as the energy that needed to be expended. So far, what I showed was that the first system is passive, that I don't need to do anything. But the second building block is also passive, and the other building block is also passive. So when I put together all of them, these two passive systems in parallel are going to be passive. All I did was to go back to your original graph. I just decompose this one into, you can move the plus signs. So I have this component which is going to be passive. And then I connect it with the feedback of a strictly passive system. Remember, I used earlier that if one is strictly passive and a feedback system of a passive, then I'm going to have some magic property that overall system is going to converge to the equilibrium point. So that means I can drive it towards the throughput I have. I cannot say that I can achieve all the throughput, but I can drive it towards the desired optimum point. Now, the question here is that driving towards the desired optimum point when there is a bad load around means continuous interaction, right? Right now I showed you one instant of optimization. So it's a continuous interaction, and then it becomes a thing. And how do we go about asking the question, how do we leverage then what we have done here to say a little bit more about different types of wormholes. So wormholes that may be out of band, wormholes that may be in band. Simultaneously, there may be multiple wormholes. So this is the first time. If you look at network flows here, I can actually combine arbitrary number of wormholes and represent it in one figure. And also develop the mitigation in one shot, rather than saying that I need to go around building the mitigation for each of them separately. So I don't need to know how many of the wormholes are there. I just need to be able to model it. Not only that, once you have modeled, you can go back and reconstruct in the form of a block kind of matrix structure, in the sense I can group a subset of wormholes together, another subset of wormholes together, and form a system. Then I can go and mitigate each of the blocks. That's just the luxury that you have. Saying that, oh, now for some reason I can take these different attacks and then probably put together into smaller blocks. It still doesn't mean that I have it primitive, but at least it allows us to take the combined model and then break it into smaller units that we feel comfortable with. That doesn't mean I show you what is the unit. So this is added property that you can do the composition. So one numerical study that was done to illustrate the effect of incorporating the mitigation and also performing this wormhole-based dynamics. So one is the detection and mechanism using the packet leash, and on top of it, setting up this. So the equation is of the type first order differential, and the gain is simply a delayed scale version. So that's the system. So it gives a plant, it sends a signal, it goes through, and it has 2 hops. Each of the hop takes 0.05 units of time, but this equivalent one is 0.1, twice the length of it. It's a simple model to just show you the concept. So these are the quantities, and adversarial drop 90% of the packets when the flow is great enough that it won't get controlled. So what happens to the system if the delta max exceeds certain level, the packet leash will be forced to the top. So here is what happens for the wormhole in the absence of packet leash. So you don't have the packet leash here. All that happens is the flow balancing system. So there are huge jumps in the system. They are unstable. The system can oscillate quite a bit, but for an instant, right? So when the split, and then it goes back to wherever it needs to go back. It takes time to recover. That's why the band is back, and then again and if you choose the lambda max, so you force the packet leash method, but in the process, what you also do is to add a very small time delay as a tolerable time delay for the packet cycle. So the system continuously goes out of bound, so range starts oscillating. This is the property for lambda, which is very small. So choosing the lambda that is of the type 0.1 gives you the system which is manageable than scale, and also it directly works with the flow balance equation. So detection helps in addition to the flow balance equation to keep the system. So this is the first. So the first set of system that I showed you is a physical equation. It's a network flow balance, and it's almost satisfying a physical quantity constraint. So you may ask, okay, this is great, but then this is actually governed by a physical system. So what about pure cyber system? You have seen malware in our system. So how do we do that? The problem that we are going to look at here is the following type. So we don't know what the malware is, what it takes place, but we can characterize the malware into 2 categories. Types that compete to get into the system, or they may coexist in this system. So dynamics that takes place is such that the type may go through, and the second type may replace the first one, and this may happen. So a set of them may find existing, others may be competing against. So mitigation here is periodically do the patching process. So now we want to ask the question, okay, patching happens on the software side. So what can we say about the patching, and also can we model this system and then understand what the process is. There have been other control models that have shown the dynamics in the previous case, like optimal control or bang-bang control, what the maximum impact would be. But here, what I want to be able to show is the dynamics of the malware transition forms the appropriate system model. So the question is that in the competing case, here is the system which is clean. At some point, it may be compromised by one type of malware, and then from here, it may take a state where another malware is obtained, and the process may repeat, and the blue lines are the ones where there is indication. Or the second model is where the malware may coexist, and intermediate state, or they may join the existing system. So how do we go about modeling this to understand? So at a very top level, you can make the case all the nodes may be identical and the network may be homogeneous. But here is the homogeneity or heterogeneity of the malware comes in. For each of the node, the neighbor node NFI, the degree of connectivity may be varying. And hence, the influence of the neighbors may be varying. So the rate into each of the node, that is not necessarily going to be homogeneous. So this is an important point where when we do the model, the rates may not be identical for patches. The second one is the rate of transition from an infection from one type of malware to go to the other one. Similarly, we want to be able to talk about the patching rate for a specific type of malware. So these are the basic quantities, and the probability of a specific node being infected by a specific malware is also identical. So this is the notion of the state that I want to be able to use. So if you look at the system, initially compromised and compromised by the malware of type 1, followed by another type of malware, followed by repeated compromise, and then it may be patched. So the governing equations of the type, the first term is the following. 1 minus means initially nothing was compromised, and then 0 3 being the type 3 is going to be compromising. So this is the uninfected to infect with the virus or malware. Now, if the malwares are computed from V to U, this is the expression of the malware transition from one to other. So you can get the three components of the computing type of malware, and the last one is the infection type of one. What I have done is to describe the dynamics, and then using the dynamics, what I want to be able to show is for each node, I want to be able to show this is equivalent to a system that I can now control. How will it go to? So here, if the two type of malwares are competing, it may either replace each other. In the scenario where they are coexisting, they may partition and be their unit. The patching or the mitigation mechanism is a feedback where the propagation is going to be monitored or moderated and controlled. This is the overall system block that I will do. The first question is, how do I create an associated energy function to be able to characterize each of these activities? Because if I can characterize, then I have overall energy function, then I can start talking about regardless of otherwise, regardless of what type of malware they are, I show you the patching rate. Otherwise, I have to go individually and show what the patching rate is there. But that's not what we want to be able to do. Given a set of malware, we want to be able to answer the question, what is the effective patching? So, from the dynamics, I have two components. One is all the state going from good state to compromised state from one type to the other, and repeat that this process may take place. Other is the patching rate. So these are the two that govern the probability of being compromised, the node I being compromised by a specific malware, which is denoted as B. So I have the expression of the malware propagation dynamic along with the patching equation. The storage or the energy function that I show you is the dynamics that takes place in the probability of being infected by a malware. If I look at the X, or the probability is the rate of transition, and look at the sphere function of it and define that as an energy. So now, what is the interpretation if we have this energy function for the malware assist? One of them definitely is an equilibrium of the good type. Other one is an equilibrium of the type where things are unstable. So these are the two things we can understand. Here is the interpretation of figuring out which one is big. Right now, there is a red state and a green state. We know that there are two states. One, everything is bad, other is everything is cleared out. So, how do we choose which one is what? Look at the following. assume all the states are good. I just introduce one bad entity or one compromise, one molecule, right? So the moment it is here, the propagation dynamics takes place and it starts moving and going into the overall system. So hence, a small nudge to the system brings it down to some other state. So that's why although the node being not infected is a good state we would like to have, it is also the unstable equilibrium point for the system. The stable equilibrium is everybody is compromised. So this is the stable one. So you don't have to do anything anymore after that. So how do you then interpret the two quantities, passivity index and then the patching rate? Patching is what you do to climb the mountain, while the passivity index is the one which is bringing you down, pulling back down, and they both have to satisfy some quantity. As long as the patching rate is greater than the passivity index dissipative, you are going to be in a good state. You are going to continue to move to a good state. So your patching rate has to be greater or equal to the passivity index. This I can figuratively come up with this statement, and the first thing you say, oh wow, I have energy, I can compute the index straightforward, then it gives me an idea what the, if you tell me what the propagation rates by adversarial method, I can approximately compute what the rates are going to be. So this is the first result. Patching rate has to be greater or equal to the passivity index. And then what is the interpretation of the passivity index with this method? Here is the interesting interpretation. I am eliminating all the notations, but some notations here. Remember, lambda is the rate from going from V to U, right? Being infected from molecule V, going to molecule U. And then here is the state of being good and going to the molecule infected state of U. So this quantity multiplied by the number of neighbors of the node I, if I define as Qi of U, this is the diagram we solve. So if the maximum of this, that gives me the passivity index. Essentially, you have the state V, V1, V2, whatever the number of molecules, and specific type of molecule, take a cut of this graph, and the cut gives you the rate at which the transition takes place, and the passivity index is the maximum rate at which it takes place. So this is the interpretation of the passivity index. Of course, we earlier said this was the interpretation of how far off it is from the passive. That was abstract, but here it translates to, I can actually tell you, if you give me the empirical rate of transition, I can tell you overall what rate it is. But more interestingly, the passivity index, actually I can quantify between these kind of networks. Right now I have coexisting or competing. I want to ask the question, which one is greater than which one? What's the order in which this is happening? So, mathematically what we were able to show is that coexisting passivity is greater than the competing, but then it doesn't give you the intuitive feeling. What we did was to then show, if I define a random walk or some kind of mechanism by which I go from one state to other, and reaching the desired state, which is a clean state, the T state, no one is infected, the node is not infected. The clean state, if I define that as a hitting time, you may call it stopping time, but this is hitting time is appropriate. So then what we actually were able to show is the hitting time for coexisting, if molecules exist together, is greater than, or strictly greater than the case that the last state is not here, then that is greater than the hitting time. So I have a constraint. The time it takes for me to clean up, that's the interpretation of it. But here we have it in terms of the rate. Here it is translated in terms of time. So for molecules that are coexisting, you take more time to clean up. Even though you may think we are sitting on the same system, it will take more time to clean up versus the. So this is the core result of this. Now, those of you who look at it and say, how do I define the patching rate and optimize? Remember I made an observation that for each node, although they may be identical network nodes, their neighbor nodes may be, degree may be different. The degree introduces the adequate amount of heterogeneity for your problem to have matching rates that are different for different virus or malware at each of the nodes. Beta 1, beta 2, beta 3 for node R. So they are different. So you double indexing, right? The beta 1 I want, 2 I 3. So it's a vector. Now, then you can ask the question that, can I make sure state get clean and then I get to the point? Yes, you can do the optimization and get to the point by doing the following. That the inequality of this type is naturally satisfied for this system, and the optimization here is a pure convex optimization that will sort of be giving you the effective passing rate in the form of vector for each of the rows. And they may not be identical. So this is also doable and we complete. You have a question? If you have a question, you can go. So here essentially this is it is satisfied because the passive system exhibits this exponential structure of the equilibrium that is given. But we can also use that to define what the gamma should be, and the gamma is a vector for each of them. So moving forward, what we are looking at is the following. Go back to this malware structure, and then we ask how to represent these intermediate stages as well as the overall attack. So how do we go about arguing this problem? So I say, oh, each of the units have some dynamics, and we don't know what it is, but they have some dynamic representation. In that case, if I want to represent the dynamics in terms of some variables, and if I can parameterize, I can get a sequence of different versions of it, variations of it at each level. I don't know which variation is that being used. That has to come from some post-mortem data to find some of them have to be thrown out and others will be valid. So this is the first step, decompose to intermediate level. We don't know how to decompose. That's a different question that we need to investigate. And if the variance can be parameterized using that primitive, that will be good, but we don't know. The second one is to look at and ask the question that how do we model the strategic interaction at each of the local states, not going outside, but intermediate state. Can we talk about the convergent state? Remember in the earlier, I said, what is the matching rate gamma? Can I compute it? Yeah, convex optimization gave me that solution. I know the rate at which the convergence takes place, and I can then decide, oh, I want to go for 90% of it, and then I jump from that interaction completely. I may not go all the way to completion. So similarly here, is it possible for us to compute the convergence rate? It's not necessarily that most of these problems will allow us to do it, but we want to be able to compute the convergence rate. That gives me an idea how long I want to be interacting before I terminate and go to the next stage. So transition between the states, this we don't know how to develop this transition properly. I mean, why should they switch and what the properties are between the one and the other. But what we want to be able to do is to compose from one domain to other so that the transition can not only go forward, but if needed, it can go back and re-enter the previous stage to explore something else. We don't know how to do that. So these are now the questions that we are looking at. And the last one is, of course, looking at the validation. The validation comes from a completely different program. DARPA has this transparent computing program, which is started to understand the advanced persistent threats. So they are actually generating and then creating scenarios. So postmortem data will come from that program into what we are doing. So putting it all together, so this is a very new ONR Martin University Research Initiative that we just started last June. So the idea here is researchers looking at different components, putting together whether we can finally come to a testing and validation stage over the next 5 years is what we are looking at. Many of the answers we have no idea. We want to solve this problem, but not to because uncharted territory for two reasons. The interactions are not just modelable using the standard economic-based utility functions and utility. So the whole idea is to re-look at this problem and say if they are not rational and the changes are drastic, what kind of model can be developed? And so summary, to introduce a passivity framework, possible operational modeling, focus on the continuous representation only, I didn't give you a characterization of entire class of continuous systems that are satisfying. That we don't know how to characterize. We have an idea that flow-based attack, network flow, and that class we may be able to, but I don't know the answer to that. So two specific ones. So future work is characterizing this class, at least in the network level, that's built as a representation. And then, more importantly, there is no mechanism or method to show that how to decompose an adversary. There have been effort in the pure crypto community with Fitman, and then after Schunter also worked on it. But I can give you the following as the best example. If you were to take any of the moving object, animal or human, and if you chop them into very small parts, you may still have primitives of them. But the thing is that each of the primitives may be useless in the sense they cannot function. The hand may not be function unless you have certain unit of it as a primitive. So you can break it down into pieces, but they may not be meaningful primitives to combine and get new versions of that. So that we don't know. That's one of the questions that would be fantastic to look at an answer. Anyone who answers that question probably will be able to make a big correction. I would like to thank this work is that of Philip's Ph.D. work. The part of the work that I presented, he also looked at games and characterized a class of games which are developed by Rivest and some people from RSA in the same framework. So the dissertation is coming out as a string of hope, this material and the others are many collaborators, and we thank NSF and all of those. These are some of the papers that are in the domain. Most of them are in either CPS or CDC or automatic control or transaction of network control system. With that, I'm happy to take any question.
Right, so we're going to lose the room pretty soon, but I wanted to present you with something to remember your time here. Bye.
Thank you very much. Thank you very much.
The Judd Department Lecturer, and this is the Alfred Thomas and Mary Judd, and we appreciate your support. If you have questions, maybe we can come up directly and ask Radha, and we'll take the session.
So my thanks to the department and also to